Hey guys, welcome to this video on recurrence relation. So here we want to solve the following recurrence relation. So we have our base case here. It says t of 1 equals 1. Again, that's our base case. And then we have t of n equals 2 times t of n minus 1 plus 3, which is our recursive case. So let's go ahead and get started here. I'm going to write down k here for our number of iterations when we're trying to solve t of n. So we'll start off with k equals 1, and we try to solve t of n. So we just have to rewrite the equation, which says t of n is equal to 2 times t of n minus 1 plus 3. All right, so now we need to figure out what is t of n minus 1. All right, so put a little dot here. T of n minus 1 is equal to 2 times t of n minus 1 plus 3, because we're just plugging in n minus 1 for n in the original equation. All right, so now to simplify this here, we get 2 times t of n minus 2 plus 3. Okay, so now we can rewrite our t of n. So this will be our second iteration here. So t of n is equal to 2 times, we're going to substitute t of n minus 1 for what we just solved here. All right, so equals 2 times t of n minus 2 plus 3. And then we have to add on our 3 from up here. So plus 3. And then let's simplify this. So we get 2 squared times t of n minus 2 plus 6, because we have 2 times 3 here. And then we have to add on that 3 right here. All right. So now we need to figure out, well, what is this t of n minus 2? Well, t of n minus 2 is equal to 2 times t of n minus 2 minus 1 plus 3, which is equal to 2 times t of n minus 3 plus 3. All right. So let's plug that back into our original equation. So now we get 2 squared times, we're going to substitute t of n minus 2 for that equation there. So times 2 times t of n minus 3 plus 3. And then we have to add on our plus 6 and our plus 3. So plus 6 plus 3. And let's simplify this here. So we get 2 to the power of 3 times t of n minus 3 plus, well, 2 squared is 4 times 3 is 12, and then plus 6 plus 3. Okay, so we're basically trying to find a general form. So for some arbitrary value k, what does t of n equal? And it looks like we have a pattern here. So it looks like t of n is equal to 2 to the power of k, because when our k value equals 3 over here, we get 2 to the power of 3. When our k value equals 2, we get 2 to the power of 2. And then when our k value equals 1, we get 2 to the power of 1 here. Even though we actually don't have a 1, it is implicit. Okay? And then we get times t of n minus k. Again, we get when k equals 3, we get t of n minus 3. When k equals 2, we get t of n minus 2. And then when k equals 1, we get t of n minus 1. Okay. And now we need to get this third part here. We have the 3, the 6 plus 3, and then the 12 plus 3. Well, that's just 3 times the summation from I equals 0 to k minus 1 of 2 to the power of I. Now I'm going to show you guys how I came up with that. Let me go ahead and back that up. So here it looks like we just have a 3. So imagine this is 3 times 1, right? Here we have 6 plus 3. So let's rewrite this here as 3 times 2 plus 1. Okay, that's 6 times 3. And then here we have 12 plus 6 plus 3. So let's rewrite that as 3 times 4 plus 2 plus 1. And then you can see the summation here. So our summation runs 1 time here when k equals 1. Our summation runs 2 times here when k equals 2. Our summation runs 3 times here when k equals 3. And they're each being multiplied by 3. So that's why we get the 3 here. So we have 3 times the summation, 3 times the summation, and 3 times the summation. All right. And it looks like they're powers of 2 because we have 1 plus 2 plus 4 here. So that's why I say 2 to the power of I. And it looked like it starts at 1. So I know that 2 to the 0 is 1. So we say from I equals 0. And then it ends. So this runs again 3 times, 2 times, 1 time. So it looks like it runs whatever number k is, right? So that's not really necessarily true. So if k equaled 3, so this would be 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3. All right, and that does not give us what we wanted here. So we actually want k minus 1. All right, so we want to stop right here. We're starting at 0. We're still running k times when we do k minus 1 because it runs up to k minus 1. All right, so that's inclusive. Okay, so that's how I got my summation. And I hope that wasn't too confusing. Okay, so now let's put a little note here. We have a summation formula, the geometric series formula. And it says from I equals m to n minus 1 of a to the power of I is equal to a to the m minus a to the n over 1 minus a. And we're going to use the same formula to rewrite our general form or our general equation. So this is equal to 2 to the k times t of n minus k plus 3 times, now we're going to use that formula here. So our m is equal to 0, so we get 2 to the power 0 minus 2 to the k, because we're using k and not n, all over 1 minus 2. All right, so now I'm going to rewrite that here. Just use the space that we have. So we're going to simplify this. We get 2 to the k times t of n minus k plus 3 times 1 minus 2 to the k over negative 1. And this is equal to 2 to the k times t of n minus k plus 3 times 2 to the k minus 1. Okay. Now, that was a lot. Let's get this in terms of n, and we can do that by using our base case, which says t of 1 equals 1. So we want our t of n minus k to equal 1. We need it to stop. We need it, we need our base case here. So what we really want is we want t of n minus k to equal 1. So to do that, we need n minus k equals 1. So that means that n equals 1 plus k, and n minus 1 equals k. All right, so now we can plug in n minus 1 for k. So let's go ahead and do that. So this is equal to 2 times n minus 1 times t of n minus 1 plus 3 times 2 to the power of n minus 1 minus 1 Okay, so this gives us 2 to the n minus 1 times t of 1 plus 3 times 2 to the power of n minus 1 minus 1. Yeah, okay. So this equals 2 to the power of n minus 1, and t of 1 equals 1, so it's just times 1 plus, and I'm going to multiply this 3 out, 3 times 2 to the n minus 1 minus 3. And now we're going to pull out that 2 to the power of n minus 1. So it's 1 plus 3 minus 3. And this, of course, is equal to 2 to the power of n minus 1 times 4 minus 3. And this is just equal to 2 to the power of n minus 1 times 2 squared minus 3. And because I'm running out of room here, I'm just going to erase this 2 squared and this n minus 1, multiply them out together, so we get 2 to the power of n plus 1 minus 3. And that's our answer there. So what is this in big O notation? So this is big O of 2 to the power of n. At least that's our guess. And we have to check that basically with induction. And that would prove that this is true. So thank you guys for watching. Please leave any likes you have, comments, questions. Don't forget to subscribe and share the video if you found it helpful. Please let me know if I made any mistakes, because that does happen sometimes. And as always, thanks for watching, and I'll see you all in the next video.